and moles of chloride. I'm assuming it was related to the lab. So in that particular experiment that he was doing on there, let me just grab something here to write with. And I believe it was, it's been a while since I read it, but I believe they took some silver metal, and I believe they reacted it with, I want to say nitric acid off the top of my head. And kind of going to make like silver nitrate. And then I think what they did is they took the silver nitrate, which was pretty much made kind of after he added the nitric acid, kind of the gross brown type fumes and stuff. And then I want to say hydrochloric acid was used, if I'm not mistaken. And essentially what's going to happen is the chloride from here and the silver from here are essentially going to come together to make this silver chloride solid that was formed. And in this sense, and when you start with the solid silver in your evaporating dish or whatever it was there, after you did all the process that's above, at the very end of the experiment, you technically would have your silver chloride that was made. So to find the mass of just the chloride, it is the difference basically between these two. So it's the difference between the mass of the silver and, was it the evaporating dish at the beginning? So it's the difference basically. You want to subtract these two. So you want to take the difference between these two values here, and the difference would be the mass of the chloride that was added basically, would be the mass at the end of the experiment minus the mass at the beginning when you just had, the silver by itself. So that's, in terms of those numbers, and I'll let you do it in terms of the calculation, but in terms of the numbers, you probably should have somewhere in that video the mass of the silver plus the evaporating dish. And at the end, you should have the mass of the evaporating dish. That will essentially give you the mass of just the chlorine part or chloride part. Does that make sense so far? So once you get the mass of the chloride part, and again, I'll let you actually use the right numbers there and do the calculation. But once you get that mass, let's just say, for example, the mass of the chloride after you do that calculation, let's just say it was 52 grams of chloride, okay? To convert that into moles, what you need is kind of like where we just stopped in lecture. You're going to need what is known as the molar mass of Cl, and that can be found on the periodic table. And if you look underneath Cl on the periodic table, you will see something like 3545. And we were just talking about that in terms of it being how much AMU per atom it is. It is also the molar mass of chlorine, which means that there are 35.45 grams. So to get from using the actual data in the experiment into moles, you want to use that periodic table and the molar mass to do so. So if we were to do that calculation, we would start from my example. And again, this is not the right number from the experiment. It's just one number I made up. 52 grams of chlorine. We would use the molar mass where the grams are on the bottom. So we're basically going to divide by the molar mass. The grams of chlorine will cancel. And if you grab your calculator there, and you got 52 divided by 35.45, gets you about 1.5 moles of chlorine in this case. So in the experiment, or chloride really in this case. So in the experiment, you want to look for, in that video, the mass of the silver at the beginning in the evaporating dish, and the mass of the evaporating dish and your product at the end. And again, Any questions on that? Yeah, so again, I feel like in the hydrate experiment, there may be multiple people that experiment for their heating for the isn't changing. So we've hit basically all of the silver chloride that would come together, and we evaporated off all the excess uh, nitric acid that's sort of left over and all that kind of stuff, that kind of aqueous solution that's left over. So for all the calculations, calculation as sort of your final mass of your product. So if those are the numbers he gave you, the 0.717 grams was basically the mass of the product by itself, minus 0.58 was the mass of the silver. So again, the difference of those two numbers should give you basically how much chloride was in silver in this case. Other questions on that? All right, another question you can answer again. Just for questions or labs, if you have question anything, experiment 7, just study assignment B, or something about a lecture, feel free to ask. You're welcome. So, Sander, the actual past recordings will be the past recordings will be actually be found not on the ConferZoom site. I know there's a space in there where it says recordings, um, because they're not uploaded to kind of the cloud and everything like that. You can find the link to the past recordings in the module section. So if you look in the module section of our Canvas site, you should see a little guy that says past recordings and stuff like that, and that will link you through there. So that's where you'll find all of the last recordings. So pretty much through the Confer's site, the Confer's section on ConferZoom section on Canvas, for our purposes, it will allow you to connect into the meeting, but all the recordings will then be posted into the module section. I can do some for the study assignment B if you want to give me maybe just a couple of the examples there. I don't know if I can do the whole, I don't want to do the entire page, but I just don't have it in front of me right now. So if you could just tell me what the molecules were, or kind of type in what they were, I could go through, I think, most of the columns that you would need to fill in to make sure. PCl5 and SF6. Okay, let's take a look at those. Let's try to get a clean page here. All right, so if we look at, for example, PCl5. So are you talking about kind of go through everything that's on there for this particular guy? So if we drew the Lewis structure, we would look at phosphorus on the periodic table. So that's group 5, right? So that's 5. And then there's 5 chlorines each from group 7 is 7. It's a lot of amount there. So that's 35. That's 40 electrons when we draw it. So again, in the center here would go our phosphorus. We would do 5 Cls all around here. Again, where we put that 5th one doesn't necessarily matter. We would then want to make, again, 1 bond from the center to each of the outside ones. And we want to figure out how many we use. So that's 2, 4, 6, 8, 10 electrons. So we still have 30 more to go. Again, we're going to fill up the outside ones until they get to that 8. That's 2, 4, 6, 8, 10, 12, 14, 16, 22, 20, 28, and 30, right? So if I'm not mistaken, now four, sorry, 1, 2, 5 guys, electrons each, so that is electrons all the way around. The chlorine is 8, so they're all exactly perfectly good. And then the 2, 4, 10 electrons, and they get right next to chlorine. Those are those d orbitals available to them. They're able to basically house all those extra electrons. So, excuse me. So when we look at this, we want to look at the electron pairs. It also happens to 5. So 5 electron pairs in terms of the electron pair geometry. I don't believe it actually asks for on the lab. It would be this triangular bottom. And what it did ask, though, I think on your sheet there is the molecular geometry or the shape, if I'm not mistaken. And again, this is sometimes just referred to as a shape. And because there's no non-bonding electrons around the central atom, the molecular geometry will also have the exact same name. So that's triangular bipyramidal. So that represents the molecular geometry name as well. I think another thing that they asked for was hybridization, if I'm not mistaken. Technically speaking, when you get to the 5 electron pairs, the question is triangular or trigonal. Usually for the 5 electron pairs, it's called triangular. And typically for your 3 electron pairs and 3 bonds is trigonal, or your 4 electron pairs and 3 bonds is trigonal as well. So usually triangular is usually used more for bipyramidal. Sometimes people will call the trigonal planar one triangular by itself without the bipyramidal. So sometimes you'll see that name used for just a trigonal planar. So when we look at this, it has our 1, 2, 3, 4, 5 electron pairs. And again, when we're doing hybridization, sometimes as we talked about last time, the easiest way is really just to count boxes. So since we have 5, that would be 1, 2, 3, 4, and 5, which means that the hybridization would be something with 5 electron pairs. Any questions on that so far? Now, PCl. So just give me 1 second. I'm just going to share for just a sec. I'll put it right back up for you. I'm just going to go look for something really quick here. Let's see if I can find it. Let's see where that go. Maybe. Actually, let me see. I think it might be in here. Where did that thing go? Here. So when we're looking for, in terms of the actual bonds, what type of bond, which was a question that was asked sort of earlier, is it a polar or non-polar bond? Again, that's what we want to look for and use in terms of electronegativity. And did they give you the values? They did. Okay, good. Okay, let me pop that up so we can take a look at it. That tells us that it is a polar bond. And really, when we look at it here, it would be going towards the chlorine. So the type of bond, which is I think one of those columns we were talking about, it would be polar, again with that difference of I think it was like 0.9 was the difference in electronegativity values. In terms of actually using those values for something like this guy here that we're doing, you could actually just use the periodic table. So earlier I just wrote on there that on the periodic table, all these guys are in the same row. And even without those numbers, we see that chlorine is right. Those bonds, or that bond is going to be a polar bond. And when we do look at sort of the last thing I think that might be on there is the molecular polarity. We could do what we talked about before. When we look at this geometry and this Lewis structure, we do not see any dots on the center atom. And since we don't see dots on the center atom, and all of the outside atoms here are exactly the same, that means that this is going to be a symmetrical geometry, and the molecular polarity here would be nonpolar in this case. I think I hit all of them, if I'm not mistaken. Did I miss any of those columns that were on your paper? Bond angle, again, bond angle is based off of the bond angle is based off of the triangle bipyramidal, and yeah, it does have that. It would be, in this case, it would be probably 90 degrees. Usually when you get those non-bonding electrons is when we see the bond angle sort of become a little bit lower than that. In terms of your other question, SF6 would be very similar. So if we go to, say, the next page here, just kind of go through that one with you as well. So if we look at SF6, sorry about that. I know how it is on your screen, but I have like a ton of boxes I have to move around just to get to the screen where I can write. But let me try here. So SF6, which I think was your other question. Again, we want to do the same thing. So the sulfur, again, is group number 6. There's 6 fluorines, which is group 7. So again, here, we would take our 6 times 7 plus 6, gives us 48. So our picture here, again, should have 48 electrons when we draw it. Again, sulfur should be in the middle, as fluorine is the most electronegative. Remember, when you're trying to decide who goes in the middle, it usually is the least electronegative sort of atom. We're going to make our single bond from the center to each of them. We've now used 2, 4, 6, 8, 10, 12 electrons. So that leaves us 36 more to go. Again, they're going to go on the outside in pairs until the outside ones are filled. And if we kind of go around, and again, at this point, we have basically 6 guys with 8 electrons around it, which is 48 electrons. This will have used up all 48 that we need. All the fluorine there is perfectly good. The fluorine has 8 electrons around it, which makes it perfectly happy. Again, as we talked about with the last one, our sulfur is able to do that expanded octet. So with its 12 electrons, are going to be perfectly fine as well. Again, when we look at the central atom, which is our sulfur in this case, in terms of electron pairs, it's got 6 electron pairs, 2, 4, 6, I'm sorry, 1, 2, 3, 4, 5, 6. And in terms of bonds, it also has 6. So again, although the electron pair geometry I don't think was on that list, the electron pair geometry here is going to be octahedral, which is what we get when we have 6 electron pairs. And again, because there's no non-bonding electrons, both the electron pair used for this guy. Let's see, types of bonds. And not hit that. Again, we want to let sulfur and fluorine, because fluorine Okay, I'm just going to stop sharing the screen for just a sec. I just got to go look for something. I'll put it back up in just a second. On that, it should take you to a page on our Canvas site where you again can sort of watch the video as it's embedded in here, I think. So again, if you click it through here, you can actually watch it. That's the actual link to the YouTube page if you need to kind of do that as well. So again, through the modules page, you'll see that little thing that says recorded past lectures, again, in the modules section. And then you could either click it here and just watch it through here if you like, or you can, you know, take the link and watch it, you know, through YouTube and stuff like that. So you can do it either way there and stuff like that. So that's where you can find all those things. Okay, so the question is it safe to assume that the molecule has lone pairs that is going to be an unsymmetrical geometry in terms of molecular geometry, molecular polarity? And the answer is yes-ish. It's not the best answer, but for the most part, yes. There is only really two guys that we talked about that will end up with dots on their central atom that will still be nonpolar, and it's the let's draw this one. It's the linear that I'll try to draw it as best I can here. That actually has 5 electron pairs and 2 bonds, and so that's the expanded octet linear. And the reason this would be nonpolar in this case is because what ends up happening is if these two guys are exactly the same, they're basically opposites of each other in a straight line. So they will cancel each other out. And then our non-bonding electrons are also very symmetrical in terms of a triangle, and they also will sort of cancel each other out. So this is one exception, the expanded. Really should have stopped that video. Hang on. Shut that down so I don't hear my lecturing over myself again. Huh? All right, let's try that again. So that linear there is going to be nonpolar. It does have dots. And then the second one is that square planar, where you basically have, very badly drawn here, the 6 electron pairs and the 4 bonds, and it makes that square planar geometry. And that square planar geometry, although it does also have dots, because this square is basically pretty symmetrical, it will also be nonpolar if, again, all these outside guys are the same. So typically, if you draw your Lewis structure and you see dots, pretty safe to say it's polar as long as everything attached is the same. The only exceptions really would be these two here, these sort of expanded octets that, although they do have dots, they will be typically nonpolar if everything's the same, because they end up actually being more symmetrical than unsymmetrical. Any questions on that? Yeah, thank you for the link. But again, you should be able to link it off of through our Canvas site. Again, in the module section is definitely where you'll be able to find all recordings, including the ones from today as well, and in the future. As I mentioned last time, it does take a little bit of time to kind of fix those recordings and get them up there, but hopefully within the next day. That's essentially the location where you can find it, is in the module section, where you can either watch it through Canvas or use the link and probably watch it through YouTube. I don't think they'll be up by today. The question is, will it be up by today? I'll do my best, but hopefully by tomorrow, sometime tomorrow, if I can't get them done, they'll be up there. Again, unfortunately, it does take a little bit of time to process it and get it fixed and up there. So hopefully by sometime tomorrow, if I don't get it tonight, I'm not sure I'll get it up tonight, but sometime tomorrow, they should hopefully be up there. I have a couple of lectures and stuff in the morning, stuff like that. So at worst, by tomorrow afternoon, it should hopefully be up there. Okay, so your question is, let's see, what's the difference between bonds? Is 0.4 exactly? Would that be considered nonpolar? Yeah, so 0.4 is typically the cutoff, Carolyn. For example, for if you look at actually the grab somewhere here. So if you look at the difference in electronegativity, for example, between the carbon-hydrogen bond, I believe carbon is 2.1, and I believe carbon is 2.5, hydrogen is 2.1. So again, when you do that difference in electronegativity, 2.5 minus your 2.1 gives you that 0.4. So that technically is still considered a nonpolar bond. The carbon-hydrogen bond is really the basis of all organic compounds, which is why the cutoff is kind of like right there at 0.4 for that bond specifically. So technically 0.4 is considered a nonpolar bond, which technically means that they're going to have equal sharing of electrons. But in reality, when you do look at it, there actually is a difference in that electronegativity, and it's actually carbon being a little bit more electronegative. So even though overall that bond between hydrogen is considered a non-polar, it truly is an equal sharing of heading to carbon, but not to an extent that there's not true sharing something like that. There's an idea of zero. That difference in length of zero implies and some people and zero that difference of zero is but some classify as zero perfect as equal sharing of those electrons as you can. Even though in something like carbon and hydrogen is still considered equal in reality, it's not really equal sharing of those electrons. Electrons are heading just a hair towards the carbon and a bond like that. So 0.4 is still considered nonpolar, overall considered by people as still being equal sharing of electrons. But you really don't get sort of that perfect, with quotes around it, equal sharing of electron until you really get that difference of electron of zero. And it, pure covalent on polar covalent as well. To make that distinction, you sort of have that perfect equal sharing of electrons. And if you do hit that 0.4, like in carbon and hydrogen, it would still be considered a nonpolar bond. Other questions on that? You're welcome.